Lesson 7.5, Proportions in Triangles. In this lesson, it starts out with a manipulative, which I love. It says the triangle shown was created by dividing one side into 4 congruent segments. So check this out. This moves, and these segments from here to here, here to here, these segments are congruent. So each of those are congruent segments. No matter how I manipulate these triangles, the segments are congruent. And then it asks you some questions about those. Example 1, explore proportions for parallel lines. So if these lines are parallel, which it shows that they are, then there are some special properties. So let's look at this problem. There's actually a couple different ways you can do this problem. The book does it one way, and I'm going to show you based on the rules I've already taught you and the lessons I've already done. There are 2 different triangles here. This is the smaller triangle, and this is the bigger triangle. So just like in previous lessons, you can compare small triangle to big triangle, base to height, big triangle, small triangle, use those proportions. So I'm going to label, we've got a 3, and we've got this full length over here on that left side. It's 5 plus 3, so that's an 8. So it says, are the sides divided proportionally? So if I have proportions 3 to 8, would that be proportional? So ln, this whole thing is 9.6. Okay, so take a second about that. We need to find LM, and we need to find MN. Well, looking at the angles because of the parallel lines, I'm going to switch colors and do this. This angle right here and this angle right there will be the same because those are corresponding angles because of the parallel lines. But this angle L is shared between both of those triangles. In fact, if I show it to you on these triangles, you can see them. This is angle L. So by angle similarity, these triangles are similar. So then we can solve. So this full length over here is 9.6. I don't have the short triangle, which is right here, that X, but I can set up my proportions, small triangle to big triangle. So let's solve. So I have 3 over 8 should equal X over 9.6. We're going to do our math over here to the right. We're going to cross multiply, and I get 3 times 9.6 equals 8X. Take a second. When I calculate this out, the 9.6 times 3, you're going to get 28.8 equals 8x. And then you're going to have to divide by 8 on both sides. It's not going to come out to be a pretty number, but that's okay. So if I divide by 8 on both sides, I am going to get 3.6. So this x right here is 3.6, which means LM is 3.6. MN, I think you can figure out based on the total is 9.6. That one part on the top is 3.6. Do some subtraction to find out what MN equals. This question asks if the segments are parallel. So let's look at this again, and I'm going to treat this as 2 different triangles, but I'm just going to try to visualize it as one now, as like one overlapping. So I have this short side, which is 5, and this longer side, which is 10. Short side, which is 6. Longer side, which is 12. So if I look at those side lengths, they are proportional. The short side times 2 equals the long side. And they have this angle, angle C, in common with both triangles. They overlap. They're sharing that. So these are similar by side angle side similarity, which means these side lengths or segments are parallel based on side angle side similarity. Side splitter theorem. This theorem is amazing. I love it. It makes everything very convenient. But instead of doing like small triangle to big triangle like I just did, it takes parts, and it only works if the lines are parallel, which they are. So these are parallel lines, which means that this part of the triangle should over or compared to this triangle part of the triangle will equal this part over this part. So that's what they are. They're taking the sections of the parallel lines on the segments connecting those. So comparing let's say the bottom part to the top will equal the bottom to the top. So it is called the side splitter theorem because it literally splits the sides of the triangles with those parallel lines. Here's another theorem. It's called the triangle mid-segment theorem. We've already done a mid-segment of a trapezoid where it was you take the two bases, the top base and the bottom base, and add them up and divide by 2. It was the average, that mid-segment of the trapezoid. But now we're doing the mid-segment of a triangle. And what that is, and you can manipulate this, look at those numbers, 6, 12. Let me see if I can get another number that's close. I can get 4. Close. 4.02 times 2 is 8.05. And it's rounding, so it might not be perfect. And hopefully you can see as you manipulate this, these lines stay parallel. But the distance or length of the midsegment compared to that side that is parallel to it, the difference of those or the ratio of those is 2. So that the ratio from the midsegment to that side length is times 2. From that side length to the midsegment, you divide by 2. And here's this formula right over here. Example 2, we're going to actually use the side splitter theorem. And remember, the side splitter is just that. It's splitting the sides of the triangle, but we're going to use the full sides. So let's look at these. So I'm going to take, it says, what is the value of x? I'm going to take this segment, and these lines are parallel, but this line where y is, this doesn't show any type of parallel symbol, so I can't assume that it is. So I'm going to take this bottom section, x plus 2, and compare it to this section from there. So bottom section compared to this full section. And so let's set up a proportion. X plus 2 compared to 12 plus 4. And I'll say 4 plus 12, just so you can see where it's coming from. That should equal x over that 9 plus 3. So again, it's this total section to right there. Total section to right there, that point T. So go ahead and combine those things, simplify. X plus 2 over 16 equals x over 12. Cross multiply. So I've got 16x equals 12 times the quantity x plus 2. I'm going to distribute that 12. 16x equals 12x plus 24. I'm running out of room, so I'm going to bring this back up here. And I'll just rewrite it so you can see it. 16x equals 12x plus 24. So I didn't do anything in that step. I just rewrote it at the top. Let's move that 12. 12x. So I have 4x equals 24. Divide by 4 on both sides. And I get x equals 6. And when you plug that back in to check, you should see that they are indeed proportional. Using the side splitter theorem, we're going to try to solve for y and for z. And I'm just going to solve all in any order, just whatever comes to you. So I already know that this right here is a small triangle because we have that parallel. And this full length is the big triangle. Small triangle, big triangle. And I'm going to separate these because we're no longer finding this stuff on the sides. So we can't use the side splitter theorem. We're using this stuff within. So for example, z is not part of the side that is split. I cannot use the side splitter. So I'm going to take this and say, okay, that small triangle is 16 from right up here, this distance. And the larger triangle on that same side, and I can measure this in different ways, but on this same side, it's the 12 plus the 4 plus that x plus 2, this whole length. And we know what x is, so you can actually calculate that out. And you can plug in 6. So I have 12 plus 4 plus 6 plus 2. Take a second, figure that out. Let's see, we've got 10 here plus 2 more, so we've got 24. So this full side length, I can cross all this out and just say 24. Now I can set up our proportion. And in this case, I didn't do small to big. I did left side to base. Left side to base. And you can do those different proportions. So 16 to z should be the same proportionally as 24 to 30. And you can solve for z from there. Once you get z, you would have x. Now you can solve for y. And when you look at all these triangles, you will realize that all three of those triangles are proportional because of the angles being the same. They're all sharing that angle Q. And the side lengths are all proportional. But so by side, angle, side, similarity, all three of those triangles are proportional. So you can use this same concept as small to big to find angle y. And you could use the smallest triangle where y is compared to the z where z is, or that largest triangle where that 30 is. You decide and set it up how you feel comfortable. Here's a corollary to the side splitter theorem. So it not only works when it's split with two parallel lines, it can be multiple amounts of parallel lines and it still works. So each section, so like this AB compared to BC, will be congruent to comparing this section, let me close this out, this section right here to this section right here. So the side splitter theorem works even if it's not an actual triangle, as long as there are parallel lines, like multiple parallel lines, it will work. Example 3 is an application problem, and it has to do with the side splitter corollary. So you see those parallel lines. It says a reflecting pool is separated by sidewalks parallel to the street. So here's Lincoln Street. Each of these segments or sidewalks are parallel. So they have these walkways in between those pools, which is kind of cool. The city wants to add an additional tiling around the pool. How much tiling does X represent? So this X right here is what we're trying to solve. Okay, keep in mind, those are parallel lines. So we can use that side splitter corollary to solve. So I can take X compared to 60 should equal 24 over 72. Now, if I'm teaching this live in class, I would literally have you turn your paper, not your screen, but your paper, and just look at this. This is like a fraction bar. So X over 60, turning your head, should equal 24 over 72. And that's exactly how I set this proportion up. Okay, same idea, and I'll get this out of the way. Same idea for finding y, because it does ask you y, or will ask you y on the next part of the problem. So set it up where you have 60 over 24, there's that fraction bar, should equal 72 over y. So if you need to tilt your head and look at it that way, that will help. So 60 over 24 should equal 72 over y. That will help you solve both of the parts of the problem. Example 4, I'm just going to walk you through it and I'm going to show you what the book has. So it says, in this triangle, NL bisects this angle up here. So these two angles are congruent. And we need to compare the ratios of, and it tells you exactly. So KN compared to MN, and it sets it up right here, KN, MN. And then compare the ratio of KL, ML. KL, ML. So here it is here. When we compare those, it actually shows that these two ratios are the same, which is awesome. So you have two side lengths that are proportional of the two triangles. Then it says the third pair, NL compared to NL, those sides, that's the same side. So it's a 1-to-1 ratio, which means these triangles would not be similar, even though they have an angle that's in the same, congruent, and they have two side lengths that are proportional. They have that one side length that is not proportional. So these triangles are not similar. This second part of example 4, the try it, it's actually asking you to compare these things based on what they give you. Are these triangles similar, or are they parallel, and things like that. So this part A asks if they're similar. Part B asks if certain angles are congruent. So look at this, try to figure it out, and keep in mind that line K, this line right here, is parallel to NL. That could help. Good luck. Triangle, angle, bisector theorem. So if you have a triangle, an array that bisects an angle, then it divides the opposite side into two segments that are proportional to the two other sides. Now, it's not saying that the triangles are similar. It's saying that the side lengths are proportional, those two side lengths. Okay, UX compared to WX is similar or congruent to UV compared to WV. My students do it a different way usually because I teach them when I do a lot of proportions. I say small to big, left to right, height to base, stuff like that. So I have my students label, and this is like the left side and this is the right side of that triangle. So I have them use the left side UX compared to the left side UV. That should equal right side WX compared to right side WV, and you will get the same answers. So if that helps, instead of doing broken side, side of the triangle, that is what this says. You can do like left sides of the triangle, compare the split side to the full sides, left and right, if that helps. Example 5, I'm going to give you the example as what I was talking about. So we'll say this is left and right. So left, right. And you can draw them as separate triangles or you can draw them together, but I'm going to set you up so you can see what I meant. So left side, I'm going to do the broken part of the left side. It's not 13. It's 13 minus that x because this side is x. So I'm going to say 13 minus x, left side, compared to the full left side, 16. That should equal right side compared to the full right side. And when you cross multiply, you will get the same answer as if you would do it the other way. So let's go ahead and multiply these out. I get 16x equals 10 times the quantity 13 minus x. Distribute that 10, bring down the 16x. I have 130 minus 10x. Subtract the 10 from both sides, and I'm running out of space. I'm going to go up here. So 16x, I'm just copying it down again. So, or add the 10x to both sides. I get 26x equals 130. Take a second, try to figure that out. Okay, when you divide by both sides by 26, you should get that x equals 5. Now it says, what are the values of AD and DC? Well, I solved for x. Now we have to take those and plug them back in. So AD is x, so it's 5. And then it says DC, which is right here. Well, it's a good thing I rewrote it as 13 minus x. So you'd say 13 minus that 5 to solve for that. All right, here's another one. Try it, number 5. So same idea, triangle, angle, bisector, but we're going to do it the way the book says, this program. So I'm going to take this broken side or split side compared to this split side, this full side compared to that full side. So let's set it up. So I'm going to say 3x minus 7 over 12. So I'm comparing these parts, comparing those parts. Should equal 3x plus 3 over 18. You will get the same answer as if you did it left side to right side, but here's just another setup, and you can solve from there. Here's the concept summary. So putting it all together, proportions are alive and well in triangles. So first you have the side splitter theorem. Remember those sides that are split by the parallel lines, those are comparing those sides. So that bottom part where it's like a trapezoid compared to that top part that it's a triangle. So those parts set equal to each other can create a proportion. Another one is the triangle mid-segment, where the mid-segment is half of the side adjacent to it, or the side parallel to it. And then the last, the triangle angle bisector theorem, you can set them up where the split part compared to the split part, full part, or do what I did, left parts to right parts. I hope that helps.